So, wrong proofs. Or solutions. And this will take about 10 minutes, then we go back to where we are with the binomial coefficients. Here's one, which I did last time here on the board. Was saying if 3a plus 2b is 28, show that, what was it, 2 divide the GCD of a and b. How many people looked at this problem since Tuesday? 1, 2, 3. What's the answer? It's not true, right? So this is not true. It's not about the wrong proof. It cannot be done. This problem asks you for something impossible. For example, when you prove something not true, we can give an example. If A is 6 and B is 5, 3 times 6 plus 2 times 5 is 28, right? But the GCD of 6 and 5 is 1. This is impossible. 2 would not divide 1. 2. Something that you have seen at recitations, at least some of you, I think 2 of the sessions figured this out, and the other 2 sessions of recitations did not figure it out. We have integers 1 to 99999. That means 5 digits max. And we have a constraint. The sum digits have to be 10. For example, 6, 0, 1, 0, 3 is a valid integer because the sum of the digits is 10. The problem asks how many such integers are there, right? So the question is how many. And the solution is we're going to build a map. This is a bijection. It's one-to-one function that says if you want to count this side, if you build a pairing, a one-to-one map, you can just count the other side and get the same answer, right? That's what this thing did. And then says, what are we going to do? So that's balls into beans, remember from recitation, right? And we say, well, this is the number of ways to throw 10 balls into 5 beans. The balls in here being 10 units, and the beans being the 5 counts that become digits. So if you imagine that integer with the beans as being the counts, any way to throw 10 balls. The reason I have 10 balls is this sum constraint is 10 in here. Right? So I know, I look at this, instead of reading it as integer, I read it as 6 balls, right, into that bin, 0 in this one, 1 ball, 0 again, and this is a 3. So if my balls get thrown 6, 0, 1, 0, 3, balls are identical. The only thing we can measure on them is counts. When we throw balls into bins, balls don't have IDs. They have counts. Bins do have ID. This bin is different than this bin. Okay. So what did we say? Every way to throw 10 balls into 5 bins corresponds to an integer. And any integer corresponds to a way of throwing 10 balls into 5 bins. That sounds the right approach. And it is the right approach, except this analogy is just slightly off. That's one-to-one pairing is not really a one-to-one pairing. Somebody who figured this out, why is that? Yes.
If all the balls end up in the same digit, we'll have a digit of 10, which is invalid.
So this way it works. Every integer does correspond to throwing balls into bins. But the other way, I think what he's saying is that there are some ways to throw the balls into bins that's not really an integer, right? So there are in here 5 extra ways, which are the counts 10, 0, 0, 0, 0, right? 0, 10, 0, 0, 0, so on and so forth. Those 5 possibilities, which are valid ways to throw balls into bins, right, do not correspond to integers. So to solve this problem, to fix this, we can count it this way, but then we have to subtract these extra 5 possibilities that are not valid integers, right? Who's with me so far? Very good. Problem number 3. This is from the homework 3, I believe, one of the problems. It says passwords of 6 spots. Here they are, 6 spots. Cannot have 2 digits next to each other. So those passwords can use the letters A to Z and can use the digits 0 to 9 with a condition. This is we call this in mathematics constraint. It's a condition that says that's invalid. Same thing like this one here, the constraint that says it's not all of them, it's only the ones with some property. So here's a wrong solution here. Is I'm gonna think of this split the 6 blocks, the 6 spots into 3 groups of 2. So don't think of the password like that, as 6 locations, but instead think of it like this. So I'm splitting it into chunks of 2. I want to do the split to satisfy the constraint. My intuition here being, every time I put a digit, right? Everywhere I see a digit, I can't put another digit next to it. That's what the constraint is saying, right? Once you put a digit somewhere, the next one cannot be a digit anymore. So what I'm going to say, well, if I put a digit, this is not a digit. So I'm going to look at this and I'm going to say, what are the possibilities for this? Well, I can have digit and letter, right? I can have letter and digit, or I can have letter and letter. 2 letters one after the other is okay, right? The constraint only saying don't put a letter next to a digit. So I can count those. This is, I say, this is the sum rule. Right? And how many of these do I have? This is 10 possibilities times 26, right? This is 26 times 26, and this is 26 times 10. So by the sum rule, the way to populate one block, so sum rule, the number of possibilities for this box is the 3 possibilities to do it correct. 26 times 10 plus 10 times 26 plus 26 squared. Because they disjoin. This cannot be that, this cannot be that, and the DD is not a valid possibility. That would be two digits next to each other. And then I say, look at my stuff here. This is 3 of these blocks. I can put anything in this block. Again, now I'm thinking of three chunks of the password. I say, this is a product rule here. You can do whatever you want in this block, times whatever you want in this block, times whatever you want in this block, is going to give you a valid password. So if this number, I'm going to call this number T, this is going to be T times T times T because I have 3 blocks and I can make any choice I want in this 2 block, times any choice I want here, times any choice I want here. Where is this off? Why is this incorrect? Somebody.
Because if you end a segment with a digit, you can't start the next one with a digit.
Okay. So my point here is to give you some typical ways for how some proofs can go off or some calculations. Very good. This doesn't always generate the correct password because this one can end with a digit. This one then can start with a digit. So I still have 2 digits next to each other. I'm not giving you the solution. This is something you gotta figure out by tonight, right? If you didn't already. Problem 4. This is from recitation, week 7, this week. So it's in your recitation paper. We didn't get to it yesterday or Wednesday. It says you have 4 reds with IDs. Red 1, red 2, red 4. Every time a problem talks to you about books or students and balls and houses and all that, you forget whether they're houses or not. Just think about they are reds with IDs or without IDs. Those books in the attestation paper, they have IDs. Book 1 red is not the same as book 2 red. They're not just 4 balls. They actually have IDs. And 6 blues. On a shelf. And there's a constraint, a condition that says, do you remember what the constraint was? Anybody looked at it? Yes.
All the red votes have to be
That's the easy part, the first one. What's the second part?
Wasn't like you couldn't have 2 red dots next to each other?
No 2 reds. 2 reds cannot be adjacent next to each other. So how do I solve this problem? Here's the wrong solution. I'm going to say choose a permutation of reds. I can do this in how many ways? 4 factorial ways. So then I have red, 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 red. In some order. For example, red 3, red 2, red 1, red 4. I'm going to look at the beans spots. Let's call it beans. Beans in between them. So my beans are, here's a bean right here, another one right here, another one right here, right here, and right here. So, what?
Never mind.
I have 5 beans, right, between those reds. I'm including a bean that's before all reds and a bean that's after reds. Those are possible spots For what? For blues, right? That's where the blues have to go. Because this is the shelf. So the reds are in some permutation. Now where can I put the blues? The blues can go in between the reds or somewhere, right? And I wanna throw the blues in there as balls, but blues have IDs. So how do I make the blues into balls? That's a problem also in homework 2 that says once you do something with IDs and you throw them in, you can throw them as balls, but you have to do something first. Remember that's problem 3 or so? Or 2, I forgot. How do I throw the blues into these spots? What do I need to do first with the blues? Permute them. So choose a permutation of blues. How many ways can I permute the blues? 6 factorial ways. Now throw them as balls. Once they are permuted, they are in a fixed order, so I can throw them as balls into beans. How many ways can I throw 6 balls, 6 blues, into 5 beans? Remember the formula? If I throw n balls into k beans, what's the formula? That will be 6 plus 5 minus 1. Choose 5 minus 1, right?
Don't you have to keep the factorials? Because it's 6 factorial, not 6.
No, that's how many ways I can order them. But each way, there's still 6 blues. It's not 6 factorial blues, it's still 6 blues. So every such way, for example, could be, when I choose a permutation, let's say I choose the permutation B5, B3, B1, B4, and B2, and there's a B6 somewhere, right? I choose a permutation. What happens if I throw them? Those are my beans here. Suppose my counts, when I throw balls into beans, the result of that operation is getting counts for each bean, right? Suppose my counts are 1, 2, 1, 1, 1. What does that tell me about the blues? How are the blues now on the shelf? This is the fixed order. Remember, I choose a fixed order. This is throwing 6 balls into 5 beans. May come out that way. Then what do I have? What would be the final result of this whole thing? The first bin is this one. So this what gets into the first bin? B5. That's that bin. And then there's red 3. And then this 2 corresponds to what?
B3 and B1.
That's the other bin, B3 and B1. Then I have the red 2. Then there's another bin here which gets this 1. This would be who? B4, right? And then there is the red 4. Red. Am I getting this right? This is the red 1. And then the other bin, which is blue 2, red 4, B6. So I say that's the way to count them, right? I just come up with a counting mechanism. I say fix a permutation of this, fix a permutation of that, look at these balls, throw them into the bins. Every such way gives me a unique way to arrange them on a shelf, such that, blah, blah, blah. Yes?
But you can't have 0, you can't have empty bins between the reds.
That's a mistake. When I throw balls into bins, may come up as 0. And that 0 is still an arrangement on a shelf, right? Problem is, it doesn't satisfy my constraint if I get a 0. Because a 0 blues will mean 2 reds are next to each other now. Yes?
So if you do it the reverse way,
Throw the reds into the,
and the bins between the blues, yeah.
maybe. All I'm saying, this is, please observe where this is wrong. It's wrong because can end up with 2 reds next to each other. Now, I agree that this maybe can be fixed to give the right answer. Yes?
Can you like start with just one ball each in pins 2, 3, and 4, and then like only draw out the 3 remaining?
Right. There are many ways to count this right. That may be one way. I want to point out here how you can get it wrong. Yes? Yes. So that's important. That's actually a very important comment. Every time you get a problem, you may say students, books, houses, chairs, oranges. You have to figure out, is he talking about something that has IDs? Is book 1 different than book 2, different than book 3? Or is he talking about something that do not have IDs, like oranges, right? Or balls. Those only have counts. You can't separate orange 1 from orange 2. You can just count it. So that you have to establish from the very beginning of the problem, even before you get a solution. Is it talking about something with IDs or without? The other aspect that you have to do is to figure out if it's in order or out of order. Whatever the end result is, putting books on the shelf, that means in order matters or not. Is it a sequence or a set? Clearly this is asking for a sequence because the order of the books matter on the shelf, right? And so you'd have to figure this out from the statement of the problem. Last one. Let's get one more wrong. Also from recitation. It says, here's a set 1, 2, 3, 4, 5, 6, 7, right? And it's asking number of sequences possible with repetition. So you can include an element from A multiple times in here. Sequences of length 20. So obviously I need repetitions because I have only 7 symbols and I want a sequence of 20 things that are going to repeat. There's no way to do a sequence of 20 with 7 things without repetitions. But there is a condition or constraint. Sequence values cannot decrease. So here's a valid sequence. Example. Two, 3, 3, 5, 5, 5, 5, that's 10 already. And then more 5s, 5, 5, 5, 5, 5, and then 7s. It's a valid sequence. It has 20 things in it. All of them come from set A, and the sequence is not decreasing. It can be equal is fine. It can increase it's fine. It can miss some of these objects. You see there's no 1 and there is no 5, 4s maybe, or there's no 6s. That's okay. This is a valid example. Question is asking how many such sequences can you create from that set A? Another valid example would be 1, 1, 1, 1, all the way 21s. That's also a valid sequence. It does not decrease, uses objects from A, and is 20 objects long. This problem is in the recitation papers for this week. It was on Wednesday and Thursday. So here's the wrong solution. I have 20 spots in the sequence. That means 19 separators. So I look at my sequence and say, what happened? Here's the sequence. Let's say this is a 10, right? This is 5 and 5. And now I have 1, 5 in here. 5. 5. And 5. I'm assuming I count correctly. This is a 20. Well, I look at the separators. I'm not including this guy at the end, and I'm not including this guy at the end. What I mean by separators, those are my separators right here. Between, if you don't count the outside ones, between 20 things, there are 19 separators, right? So let's call them separator 1, separator 2, up to separator 19. And the positions maybe will be location 1, location 2, up to location 20 in my sequence. The way I'm going to think about it is to say, I'm going to choose the separators where the sequence increases. The separators that I'm looking for are these ones that says increase the sequence. So I'm choosing 6 separators. That is where sequence increases. This sequence either stays the same or increases. So the separators I'm going to pick are the ones that sequence increases. And the reason I pick 6 is because there's 7 values possible. So it can increase 6 times. So for example, I know how many ways can I choose 6 separators out of 19? Is that a set or a sequence? When I say choose 6 separators out of 19. Set. How many ways to do so? 19, choose 6. I'm choosing 6 out of 19. Then what I'm going to say here is if my choice set was a separator S3, S6, S10, S12, those are the separators 16 and 17. That's possible to choose those. Here are the separators. That's where the sequence increases. Then I have a unique determined sequence. That is, S3 tells me there are 3 1s, S6 tells me there are 3 2s. This is 4 spots between S6 and S10, so that's got to be 4 3s. Between 10 and 12 there's 2, so that's going to be 2 4s. Between 12 and 16, that's going to be 4 5s, right? Because between 12 and 16 there's 4 spots left. And between 16 and 17, there's got to be 1 6. And the rest of them, how many 7s are after that? If this is S17, how many more spots do I have to get to my 20? The sequence has to be 20 long. So where is S17? This is S17 right here, right? If S17 was chosen, the remaining chunks, how many spots are there? 3. So there's got to be 3 7s. So what this is saying, as soon as you choose 6 separators, any 6 separators will create a unique sequence. Because the separators, those 6 separators, will determine how many 1, 2, 3s, 4s, 5s, 6s, and 7s you have in your sequence. So what are my choices? How many possibilities are here? My only choices were in choosing those separators, right? 19 choose 6. So therefore, every choice of separators gives a unique sequence. Therefore, I've got 19 choose 6 sequences. Where did I get wrong? Somebody else, please. I know, you guys know everything. Somebody else. Where did I get wrong?
You don't have to use all of the digits. Like, you just can't decrease. So you theoretically could have one number.
But is this, here's what she's saying. If you do it this way, you guarantee to have at least 1 1, at least 1 2, at least 1 3, at least 1 4, at least 1 5. Is that true? Every way to create 6 separators, this way, in this way of choosing them, is it guarantee 1 of each kind?
So sure.
I think it is. I think this way of doing it guarantees, because x12 and x16 are always going to be 1 unit apart. They're going to leave something in between them and something after. How about this one? If this is S1, am I guaranteed to have at least one 1 on the left side of it? Yes. So that would be like a nice method if that would have an additional constraint. If I have an additional constraint that you need at least a 1, a 2, a 3, that makes the problem harder actually, then maybe that would be the way to count it. Because this way of counting it ensures at least 1, 1, 1, 2, 1, 3, 1, 4. And that's obviously not what the problem is asking. How many people follow me here? Hands up. Okay, so you guys have about 4 days to speak this language. So the reason it's wrong, because it's not necessary to have each symbol. So maybe you can fix this proof. Maybe you can inspired by it and say, let me say, this idea sounds good, but how do I fix it so I generate all the sequences? Right? There was some other questions here? Again, my point here is to show you why this doesn't seem necessarily like a bad idea, bad approach, but overall it doesn't give the right count. So sometimes you start an idea, the idea might be correct, and then you get it a little off, you have to fix it. Those are my five examples for how a proof or a calculation can go wrong. And you should take all 5 of them and fix them, get the right answers. So now we're going to continue to where we are with the binomial coefficients. Again, please take those 5 things at least and try to get the correct answer on all of them. So we are at something called binomial coefficients. So here's a Pascal formula that says n plus 1 choose k is n choose k plus n choose k minus 1. We proved this last thing Tuesday in class. We did this proof, and I also did it again at this recitation. I'm going to do it one more time because this formula is essential for this entire chapter. This is not proof. This is a partition rule calculation. That is to say, if I have n plus 1 objects, let's call them from object 1, object 2, up to object n plus 1. The way I can choose k of them, I split this by partition into 2 possibilities. These are all choices that include the first object, and these are all choices that do not include the first object. These are my objects. The reason this is a partition, when I'm counting how many ways can I choose k out of n plus 1, all these ways are the results of this. The result is a set of k out of n plus 1. That was n plus 1 choose k does. Chooses k things as a set out of n plus 1. What I'm saying, those sets are of 2 kinds. The ones that include this first object and the ones that do not include that first object. The reason it's a partition is because any set is either here or here. There's no other possibility. And these are disjoint parts. No set can be including this object O1 and also not including it. How many people with me? This way of thinking about problems will become later on, not in this class, but later on, divide and conquer, a strategy to implement computer algorithms. How to take a problem, break into subproblems within a computer, not with mathematics. Solve the subproblems and then put it back to a solution. So this is critical for you to understand this kind of principle. You heard of knapsack problem? That's exactly the way to think about it, to solve it. So this is a partition. Now I can count how many choices I have with this object, sorry. So in here I have object, this object 1 is fixed. By then I need how many more? I need k minus 1 more. So the ways I can pick the rest of k minus 1 once this object is in the set, that would be I pick k minus 1 out of n. The reason is out of n is because I have n plus 1 total, and I already picked 1. So the rest of k minus 1 has to be picked out of the remaining, this is the remaining n objects here. Because this one, it's already in. This other set, it's not O1, but still has k more. The reason this one has k more is because all sets that are resulting here has to have k objects, and O1 is not in there. It has to contain k objects without O1. So the number of possibilities here is n choose k, because I have to pick k out of the remaining n. Since O1 is not allowed, I only have n options. So that's the Pascal formula, and this formula allows us to compute these binomial coefficients. This is n choose 0. So if n is 1, this is n choose 1. This is 1 and 1. Right? When n is 2, n choose 0 is 1, n choose 1 is 2 choose 1, that is 2, and then n choose 2 is 1. When n is 3, how much is 3 choose 0? 3 choose 0 is 1. How much is 3 choose 1? 3. How much is 3 choose 2? 3. How much is 3 choose 3? 1. How about for n equal 4? It's 1. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4. And n choose 4 here will be 1. Let's do one more. If n is equal 5, this would be 5. Oops, sorry, 1. Then we get 5. What is this here? 10. 5. 1, right? This is n choose 5. So, where was this formula at work? This formula, you can see it in here, 1 plus 1 is a 2. That was the formula for n equal 1 and k equal 1. 2 plus 1 is this 3, 2 plus 1 is this 3. 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4. All these calculations are applying this formula effectively for a given n and k. How about here? 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4, 10, 4 plus 1, 5. Because you can see how for every k you pick, that's any value here, this is n plus 1, this is n, this is going to be the result of previous two terms above it. But now I want to go even further and say, what happens with the binomial x plus y at n? And here x and y are variables, and what this really is opening up parentheses. So, because I have 2 terms times 2 terms times 2 terms times 2 terms, when I open parentheses, how many total terms are going to be there if I open all parentheses? 2 to the n terms total when I open the parentheses. But I want you guys to think about this in a different way. What's each term? So the other observation which we did last time is each term has degree, total degree, n. That is, it's x at some power and y at n minus that power. No matter how you open these parentheses, every term will be a product of n things, right? And the way you get n things is you pick something for either x and y from the first parenthesis, then you pick either x and y from the second parenthesis, all the way to a choice of x and y from this parenthesis. And if you pick k x's, you must have picked n minus k y's, because you have n parentheses total, right? So this corresponds to k choices of x and n minus k choices of y. Right? Again, I want you guys to think about it in this way. The way to open up this to get the final result is to choose either x and y in here, choose either x and y in here, choose either x and y in here, do the product. Every time you choose k x's, doesn't matter where, and n minus k y's on the other parentheses, you're going to end up with this term. So in how many ways, if I look at, for example, k equal 3, the term is x cubed y to n minus 3, right? How many ways would I obtain this term? There are 2 to the n total terms. And how many ways can be this obtained? How many of these products choose exactly 3 x's and minus 3 y's? I could do x times x and the rest of y's. Or I could do x, y, y, y and the rest x's. That would be, x, all the y's and then x and x. That would be the same term. Did everybody see that this term is going to be obtained more than once? Hands up. When I open those parentheses, this term is going to appear more than once. There's multiple ways to get 3 x's and the rest of them y's, right? How many ways are to get 3 x's and the rest of them y's? What does the choice come down to? How many of these options of opening parentheses will result in this term? So how many? You say choose 3 because it essentially comes down to choosing 3 x's out of n parentheses. You choose the 3 x's, the rest of them will be y's. So I have n parentheses, parentheses 1, parentheses 2, parentheses n. I want to obtain this x3, y to n minus 3. Comes down in how many ways I can choose which parenthesis gets the x and which parenthesis gets the y. And since there are n parentheses or factors in here, I choose 3 of them in that many ways. How about an easier term? Still at, this is k equal 0. X at 0, y at n. How many ways can I get y at n? Somebody else. How many terms, when I open this parenthesis, how many terms are going to be y times y times y times y and no x at all? There's only one way to do that. Just pick a y in every single parenthesis. So there's only one way. One time. That corresponds to the coefficient n choose n. N choose 0, sorry. N choose n. 0. Depends how you look at it. How about x to the n? How many ways to get x to the n? That is x times x times x times x n times. How many ways that's going to show up? One time, the same way, right? It's only one way to get x times x times x n times. So let's do that in here. When we have x plus y at power 1, this is x and this is y. There is one x and one y. Right? That's x plus y at power. Power 1 means x plus y, so this is a factor. This is x plus y squared. Right? So who's this one? This is x squared. This is y squared. And what are the two corresponding to, what terms appear twice when I open up the parentheses? Who is x plus y squared, by the way? You guys know the formula? X squared plus y squared plus 2xy, right? So the xy appears twice. How about in x plus y cubed? How many x cubes I'm going to have? When I open this parenthesis, this is x plus y times x plus y times x plus y. And how many ways can I get x cubed? Only one way. In how many ways can I get y cubed? Only one way. In how many ways can I get x squared times y? 3 ways. And xy squared also 3 ways. How about x plus y fourth? There's only one way to get x to the fourth, because that will correspond to each parenthesis, getting the x out of it. There's only one way to get y to the fourth. That corresponds to every parenthesis produces the y, and then it's y times y times y times y times y. What is this for? This is x cubed y. What is this 6? And this 4? How about for x plus y to the 5th? X to the 5th, x 4y, x 3y squared, x 2y cubed, x y fourth. Of course, there's a plus between them. So there's only one way to get x to the 5th. That is getting x in every parenthesis and multiply it together. There is 10 ways to get x3y cubed. If I am to look at this formula here, this is actually x plus y times x plus y times x plus y, x plus y, x plus y, right? It's 5 parentheses. Where this x3y cubed, x cubed y squared comes from? I could get it from this x times this x times this x, because I need 3 x's, and then those 2 y's. Or I could be this x times this x times this x and the remaining y's. Or it could be this x times this x times this x and the remaining y's. There are 10 ways to get this x cubed y squared, because there are, this is really cool.
5 different
This is 5 choose 3. There are 5 choose 3, that is 10 ways to pick the x's, and the remaining ones will be y's. Okay? Now, this is a mechanical expansion that does not put values on x and y. It's a polynomial expansion. X and y remain variables, and this formula will be true for any x and y. You can replace any x and y in it, then you get the statement, because the expansion will work for any values of x and y. So there are 2 particular cases very important to us. There are many relations and equations that you can obtain from the binomial formula. But two cases are extremely important. x1, y1 gives 2 to the n, that's x plus y to the n, is n choose 0 plus n choose 1 plus n choose 2 plus n choose n minus 1 plus n choose n. So the general formula, by the way, let's write it here. I think we put it last time. The general formula is x plus y to the n. That's the binomial formula. Is n choose 0, x at 0, y at n, plus n choose 1, x at 1, y at n minus 1, plus n choose 2, x at 2, y at n minus 2, plus the last term is n choose n, x at n, y at 0, which you can write again as a sum. You guys know the sum? K equals 0 to n. K is this index. Is n choose k, x at k, y at n minus k. So a sum with indexing like this writes a general term, right, in k, and then for k equals 0 is this, for k equal 1 is that, for k equal 2 is this, so on and so forth. That's how summation works with an index. K here is the index of the sum, and every one of these terms become either that or that or that for different k's. And the sum tells me I have to get from k equals 0 to n. K equals 0, I get this term, k equals n, I get this term. So this is the general binomial formula. Now this is a particular case. How did I get 2 to the n? Where's 2 to the n coming from? Yes.
1 plus 1.
1 plus 1. 1 plus 1 to the n, I get 2 to the n. And how about all these terms? N choose 0, where is that coming from? This is n choose 0 from here. Why don't I have an x and y at all? Because they're 1, so 1 doesn't matter. The next term is n choose 1. Again, I don't have the 1s because 1 at the power times 1 at the power doesn't do anything. So that's why I didn't write them out. I get that formula. What happens if I get x equal 1, y equal minus 1? What do I get now? Left side is? What's x plus y at n? 0. This is n choose 0, right? Actually, let's do it the way we wrote it there. Let's do minus 1 and 1. N choose 0, it's going to be multiply with what? Minus 1 at 0 times 1 at n, right? Because x is minus 1 now, so we got to be careful with this x, which is minus 1. Minus 1 at even powers will be 1, and at odd powers will be minus 1 at odd powers will give me what? Minus 1. So this will be, the next one will be n choose 1 times minus 1 at 1 times 1 at n minus 1. And the last one would be n choose n minus 1 at n, 1 at 0. So if you look at this, it's actually alternating signs. This one is certainly a plus sign because minus 1 at 0, that's an even power, that's a plus. This one is certainly a minus because minus 1 at 1, it's a minus. The 1 doesn't do anything. 1 at any power, that's going to be 1 everywhere. But this is alternating signs. The next one will be n choose 2 minus n choose 3 all the way. And the last one, it depends what sign do I get. It's n choose n, but then it's minus 1 at n. So that means if n is even, the last one will have what sign? If n is 20, the last sign will be plus. If n is 35, the last sign will be minus. It's alternating depending how many terms I have. So this is a good thing to know, that this is a 0. So we can apply binomial formulas in several ways. And I have a particular way I really want to apply it. I think people do all kinds of crazy stuff with it, like how do I compute 11 at the power of 5? It's 10 plus 1 at 5. And then I apply the binomial formula to get 5 choose 0 times 10 to the 0. The 1 doesn't matter. I'm not going to write the 1 because this is x equal 10 and y equal 1. 1 at any power will be 1, so I don't have to worry about it. Plus 5 choose 1 times 10 at 1, plus 5 choose 2, 10 at 2, plus 5 choose 3, 10 at 3, so on and so forth. Now this is easy to add up because these are units, tens, hundreds, thousands, so on and so forth, so they're easy to add up. Makes it for a nice formula to how to get 11 at the power quite easily. Maybe you can do one with 9 at the power by thinking 10 minus 1. Right? If I want 9 at the power, I get 10 minus 1 here, expand it, and then maybe I can do that. Now, the one that I really want to work on here, I want to go back to something we did before, last time. It was called inclusion, exclusion. Remember we did it for 3 sets? How did it look? Inclusion exclusion refers to computing the size of a union of sets. It gives the size of union. And the formula, anybody remembers the formula, was I take the 3 sets, then I do what?
Subtract the
Idea being that those being counted twice, so I have to take them out once. However, I take them out, some of them I take them out too many times, so I have to put back in. Right? Very good. How would this look if I have 4 sets? How would this principle work for 4 sets instead of 3? What do you think is going to happen?
Do the same thing, but you also add.
I have to add the d here.
Yeah.
I have to take out more intersections of 2. That would be what? A intersect D, B intersect D, and C intersect D. Right? This is the other intersection of 2. When I add up the intersections of 3, there's more intersections of 3. Like, for example, who? B intersect D, and then A intersect C intersect D, and then B intersect C intersect D. Right? Those are all the intersections of 3, which I'm adding them back up. But now what?
Subtract.
I have to subtract the intersection of all 4. Right? That would be the analogy. I'm not saying it's correct. I'm saying I just mechanically went from a formula with 3 sets to one with 4 sets by trying to get that same principle. Add all the units, then subtract the intersections of 2, add back the intersections of 3, and subtract the intersection of 4. And if I have 5 sets, I'll be adding up all the sets, subtracting intersections of 2, adding the intersections of 3, subtracting intersections of 4, and adding back the intersection of all 5, maybe. What we want to do now is to prove this formula in general for any number of sets. So how would it look for n sets? Let's say those sets are A1, A2, all the way to AN. How does this formula work in general? We want the size of what? All the union, right? A1, union, all of them is. We want the add up the sets sizes, take down the intersections, What's the last intersection of 2 in this order if I do it in order? Yes.
A at minus 1, A.
Then we want to put back intersections of 3. What's the last intersections of 3 to put back? Somebody else? If I enumerate them in this order, what's the last intersections of 3 I have to put back? This is all intersections of 3. So it's 3 sets. This is sets, separate sets like individual sets, intersections of 2 of them. What's the last intersections of 3 of them? Yes.
A to the n minus 2.
And this will go down. The next set is minus. This is A1 intersect A2, intersect A3, intersect A4. The last one will be n minus 3, intersect n minus 2, intersect n minus 1, intersect n. And keeps going until the last one, it's either plus or minus. Because it alternates. Plus, minus, plus, minus, plus, minus. Depends how many chunks we have. The last one will be what? What's the last term in this formula? What is this? How will this? This is for 4 sets, but for n sets will be what?
The intersection of all of them.
Very good. The only thing we don't know is the sign. It's plus, minus, plus, minus, plus, minus. Depends how many of them, how many of those chunks are. But for each chunk, I want to know the count. What's the count here? How many things I've counted? How many individual sets are there? Somebody else. A1 to A, that's easy, count is n. How about intersections of 2? What was the count? How many intersections of 2 are here? This whole sequence here, minus, 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 minus. How many minuses are on this line? N choose 2, because there's n choose 2 ways to choose 2 out of n. Right? How about the count here? How many intersections of 3 are on this line? N choose 3, right? Because there's n choose 3 ways to choose 3 out of n. All the way down, this will be n choose 4, because intersections of 4. This would be n choose n, which is only 1, because there's only one way to choose all n of them. So those binomial coefficients keep appearing. But now we really want to prove that this is true. So we prove it the same way we prove the formula for 3. We prove by picking one element. We're going to say that's x. That is in sets A1, A2, up to say AK. So I pick an element in the union. This belongs to the union of the sets. But it doesn't mean it has to be on every single set. It's in some of them. Some elements will be only in set A1. Some others will be only in sets A2. Some others will be in A1 and A2, but no other sets. Some others will be in A3 and A7 and A77, but not in other sets, right? So I say pick an element, any element, and here's the sets that that element is in. Now this, I put them in order, but it's the same if this will be out of order, A2, A5, A77, and A100. Right? It could be all of them. There are some elements that are in all those n sets, but it doesn't have to be all of them. I want to see how many times, on the left side, everything has to be counted exactly once. So what I'm going to do here, I'm going to look at this formula and say, how many times the right-hand side, so my question is, how many times x is counted on the right side? The right side of what? What do I mean by right side? Or right hand side, sometimes people say that, right hand side. When I'm looking at an equation, what's the right hand side? This side. So my purpose is to count x exactly once. That's the meaning of a union. In a union, that x, which could be any x, because I pick one at random, has to be counted twice. But instead, I'm counting it that many times. So what I'm going to do here, I'm going to say, okay, how many times we counted x on the right-hand side, meaning in this monster case? Well, let's do it line by line. X, keep in mind that x does not appear in all sets. Only in A1, A2, up to AK. Okay? So, how many times x has been counted on the first line? So, first line. How many counts of x? If x appears in sets A1, A2, up to AK, how many times have been counted here? K times. There are n sets, but only k of them contain x. So this is k from sets A1, A2, up to AK. How about the second line? Second line counts the intersections of 2. In how many intersections of 2 x was in? What are the intersections of 2? Intersection of 2 that contain x. Not all intersections of 2 will contain x, because x is not in all the sets. What are the intersections of 2 that contain x? A1 intersect A2, A1 intersect A3, all the up to AK minus 1 intersect AK. All the intersections of 2 out of these sets will contain x, because x is in all of them. Every time you intersect 2 of them, x is going to be in there. What happens between one of these sets and some other AN? If I intersect A3 with AN, do I get x in there? Or not? Hands up who follows me. Be courageous so I can see your hands. Hands up who follows me. Okay? So if you don't follow because you are on Facebook, that's okay. We like Facebook. I love Facebook. I don't have Facebook. My wife has. So I use hers. If you're on Facebook, we respect that. But if you're not on Facebook and you're trying to pay attention, this is a great time to tell us why you don't get it. So what we're doing here, we're taking an x that is in some of these sets. Because every x in the union will live in some of these sets. Maybe one set, maybe two, maybe all of them. Let's say those sets are those ones here. We're trying to count on the right-hand side how many times we've counted, sometimes with plus, sometimes with minus, this x. So on the first line, how many times we count x? We counted once for each set that x is in. That is the k sets. Every one of these k sets will produce a count of x with plus. Should say there, we have plus k, right? Because this is plus sign. On the second line, we have minus, but how many pairs of a's contain x in them? There are k sets that contain x, and n minus k sets. These sets contain x, and these other sets do not contain x. This line has all the intersections. Some of these intersections of 2 will contain x in them when an intersection of 2 contains the x. What's the condition to get x in an intersection?
When
Both have to contain x. So out of these n choose 2 intersections, how many of them will contain x? How many of those intersections of 2 will contain x. How many ways can I choose two a's that both have x? Because to get x in the intersection, I need, yes, k choose 2. This is minus k choose 2. Because the intersections that contain x will have to be between sets that contain x, which is a1 to ak. Any other intersection, some set in here with some other set that's not from 1 to k, will not contain x. Hands up again. Okay? We are in the master level now with this inclusion exclusion principle general formula. Well, how about in here? So that's minus k2, so this is plus k minus k choose 2 because that's how many intersections of 2 contain x. In this line, third line, how many intersections of 3 will contain x? In how many ways can I pick 3 sets, all 3 to have x? It should be easier. That's a plus k choose 3. How about the fourth line? How many ways can I choose 4 sets that contain x? K choose 4. What sign is that? That's going to be minus because those ones are with minus. So what's the last line? At some point x will die. X will not going to go all the way down. What's the reason x does not appear in the last one?
Because only k elements have.
Some sets will not contain x, and if I intersect all of them will exist. So what's the last line where x still appears? So we're going to say here last line for x, that x is still in there. What's the last line that contains x somewhere? No. Yes. The kth line where I have intersections of k. What's the reason that's the kth line? What's the reason that when I get intersections of k, I still get x in some of the terms?
You can have an intersection of A1 to A2.
This intersection of all k of them will produce the x. How many times? So the intersection A1 intersect A2 intersect AK, that's one term on that line, the kth line, will produce x, will count x. How many times? Once. So that once, I'm going to write that once as k choose k, which is 1, right? K choose k is 1. But what's the sign? Is it a plus or a minus? Depends on k. That's going to be minus 1 at power k or something like that, right? Depending if k is even, it's going to end up with a minus, and it's k plus 1. Or k minus 1. And if k is odd, the last one is going to end up with a plus. It's going to be a count of 1. K choose k is 1. The only question is it going to be minus 1 or plus 1? So now, we know those counts. All right? So let's write them down, the counts of x. Right hand side of inclusion exclusion. Let's add up those things. Counts of x. Remember, this was any element. I pick one at random. X is just one in the union, and those are the k sets that contain it. K could be 3, if there are 3 sets, or maybe there's 7 sets, or maybe it's all of them. What are the counts I got? I got k choose 1 minus k choose 2 plus k choose 3, right? These are the counts. The first line counts xk times. Second line subtracts x, k choose 2 times. Third line adds k choose 3. Fourth line subtracts k choose 4, all the way to this value. So plus da 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 until minus 1 at k plus 1, k choose k. That's summing up the counts for x. Hands up one more time. Who followed this? Great. Now, what is this? How do we get an answer here?
It should be 1,
Why?
because we want to count everything as 1.
If that's correct.
Yeah.
That's what we want to prove. It's 1. How do we prove this whole thing is 1, right? That's what we want. Want. When we say want means we didn't prove it yet. That's our desire here. To get it to 1. Why is this 1? Yes.
So you know that they should cancel. Like k choose k is the same as k choose 1. K choose 2 is the same as k choose k minus 1 or 2. One of those. And then
That's a way to do it. How about I just apply this formula right here? What's the difference between that sum and this sum? This has all the, this is n, that's k, that's easy, it's n versus k. Let's imagine this formula with k. Let's write it with k. K choose 0 minus k choose 1 plus k choose 2 plus minus 1 at k, k choose k. What was this formula saying? This whole thing has to be 0, right? So what's the difference between these? What terms from here, are all the terms from there to there? Or is there something missing?
K choose 0 is missing and the signs are swapped.
Right, so this is the term that's extra in here. All the other terms, they appear in there, but the sign is reversed. So if I reverse the sign and add k choose 0 to it, so this formula, I'm going to change the signs. I do minus k choose 1 plus k choose 2 plus minus 1 at k, k choose k. The reason this is reverse sign is whatever k plus 1 sign gives me, k will give me the other sign. Because it's, one is even, one is odd. And I add k choose 0 to it. I know this is a 0 because that formula tells me this is a 0. So I also know the value of this guy. This is what? K choose 0 is what? 1. So if 1 minus my whole sum equals 0, what was the sum? That means the sum of those counts in the inclusion, exclusion right hand side must have been a 1 because 1 minus it is 0. Which proves that for any x, this formula here counts that x exactly once, which means this is a valid count for the union. Now, of course, this is not in the regular section, this proof. It's advanced.
Again, the
Which one?
kth line.
The kth line is the last line that contains x. What's the reason for that? Why if I move one more line to intersection of k plus 1s, there is no more x? Why?
Because it'll be an intersection of.
If I have k plus 1 sets, at least one of them will not contain x. Because x is only in k sets. If I go to k plus 1, no matter how you pick k plus 1 sets, you get one without x or more than one, and then no more x's. On that kth line, there is one of these intersections that still has x in them, which is exactly the intersections of this k. The intersections of other k, some from here, some from there, will not contain x, but x will appear one time in that intersection. And the sign, it depends on whether it's an even or the plus line or minus.
So how do you know the, like, I can't see the, so it's minus 1 to the power.
Right, so we don't know, depending on the k, even or odd, if that's a minus or plus. But we know it's k choose k, it appears one time. One time because it's only one intersection of k things that has x, which is exactly a1 to ak.
So I just don't know, like, how you got the power.
This power? This power is only for the sign. Minus 1 at the power, it's either minus 1 or plus 1, depending whether I get the plus line, minus line, minus line, depending on what line k plus 1 happens to be, that's either a minus or plus. often we use a sign, -1 at the power, just to write the sign. This whole, what she's asking is, what's up with this? This is only the sign. It's not really a power like -1 multiply k plus 1 times. I'm only using this to represent the sign. Because -1 at odd powers will give me the sign minus, and at even powers will give me the sign plus. And that's often, you're going to see in algebra, with signs alternating, people using the notation -1 at some power. They don't need to multiply -1 with themselves. All they need is to get alternating sign plus and minus. That's how you get them, with powers that are alternating, even odd. So that's inclusion, exclusion principle in a general form. And what I thought we can start doing, now we're finally done with the theory for this module. This is the last piece we need. Yes?
So I have a question about that.
Sure.
Here we said we have an x in A1, A2 until AK. Those don't have to be in order, do they?
Yes, so that's a way, that doesn't restrict the generality. He's asking, the way it worked for you was convenient because x was in the first k sets, but I could find an element that's in k sets, just not the first k sets. It's in A1, A3, A7, A11, and so forth. I can reorder the sets to be the first k, or I can redo the reasoning specifically for A2, A3, right? The counts on the first line is still going to be k, because there's k of them. The count in here is still going to be k choose 2. Even though they're not the first k, there's some other k sets. It's k choose 2 intersections that will produce it. And here's going to be k choose 3. They're not the first k choose 3, but there's some k choose 3 intersections that produce -1. And the same thing, on the last line, there's going to be an intersection of exactly those k sets, A1, A3, A7, 11, so on and so forth, which is not the first term, but it's somewhere in the line. And after that, x dies, because any intersection of k plus 1 sets will have no x in it. So the reasoning works for any x, even if this ordering is arbitrary anyway. I could have picked any order I want of these sets. That's actually a good way to do proofs. Pick an x, I know it's in k sets, and I'm going to think, to make the proof easier, I'm going to assume this is the first k sets. And I want to see if that loses generality somehow. Am I proving a particular case? No, I'm still in a general case because I can reorder the sets to put those sets I want, the k sets I want, as the first k. Reordering the sets wouldn't change the formula, right? Because the formula is symmetric. Whatever it does for set A1, A2, and 3, does also for 2, 4, and 6. So by reordering the sets, I keep the formula just to different indexes. It's a good technique to say, I'm not losing generality, but I'm assuming it's the first k to just have an easier way to think about it. So we're finally done with module 3 with the theory. So what I want to show you for the next 15 minutes today and for the whole class on Tuesday, some more fancy counting problems, the kind that are not so immediate. So I would like to do 3 today if we have time. And we'll do more next time. So those are counting problems that require some thinking. Actually, the first one's easy. N choose P plus Q times P plus Q choose Q is N choose P times N minus P choose Q. Why is that true? We only need to spend 1 minute of this. Well, you could open it up with factorials, right? And then check it out with algebra. I mean, if this is true, the factorial should cancel out and be okay, right? Can we do a conceptual proof of why this is not with factorials? Somebody else. Can we do a conceptual proof? I know if I write it in factorial for n factorial, divide by p plus q factorial, n minus p minus q factorial, blah, 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 should cancel out if it's true. And they will cancel out. But what about without factorials? How about n is 110 students? P is the size of basketball team. And and Q, say this is like, how many people play basketball? About 10? I don't know, 15 in a team? I mean, I know there are only 5 at a time in a court. And Q is the size of the football team. How many people are in a football team? Let's just say 25. I don't know football, so maybe I get this wrong. What is this doing here? The left-hand side. It chooses out the students in the class. What is this? Who's P plus Q? Is the sports together. Right? It's saying basketball plus football. That's all the people who play sports. So what is this? In how many ways can I choose the total people who play sports, which is 40, right? And then what is this? Out of those 40 people that play sports, I'm going to choose what? How many play football? And the remaining ones will play basketball. So that's a way of choosing a football team and a basketball team. It's saying choose everybody who plays sports first. And now I got 40 people that play sports. Out of those 40 people, now I choose the football team, and the remaining ones will be the basketball team. Who follows me? What is this doing here? Takes 110 students and first picks, who's P? The basketball team. And then he says, what's N minus P? The remaining ones, I'm going to pick what? The football players. The reason they're equal because both the left-hand side and the right-hand side count the same thing, which is what? Ways to choose a sets. Set 1 for basketball and set 2 for football. Because they count the same thing, they are the same. That's a useful mechanism to prove formulas, to say the reason those two are the same is they count the same exact thing in 2 different ways. Recap. This is saying choose the whole sports set first. And from that set, choose one of the teams, say the football team. The remaining one, P, will be the basketball team. Is that the correct count for how many ways can I pick a football team and a basketball team? To say, choose the sports people first. Out of that, split it into basketball and football. And another way to count the same is say, choose the basketball team first. And out of the remaining students, choose the football team. Is that a valid way? The product is because any ways to choose the basketball times any way to choose the remaining football gives me a way to count the 2 teams. And this one is also product rule because any way to choose the sports team 40 times any way to choose out of that one of the teams gives me a unique way to choose both teams. Okay? How about one that says I have a grid. Starts from 0, 1, 2, up to n, 1, 2, up to n. And I want, it's a grid, so it's everything. How many ways are to start from 0 and end up in position mn? By I can only move right, and up. So these ways, you cannot go down, you can go around. You take a cap from here, you want to get here, there's several ways to do that, right? You can go this way, and then this way, and then that way, and then that way, and then that way, and then that way. right? But I could go, maybe, that's one way to go. Another way is up, right, up, right. That's another way to go. Right? How many different paths are there? That's in Manhattan. If you have been to Manhattan, everything is either north-south or east-west. So the way to go from here to here is to paths on the grid. You don't want the cab driver to go backwards, go back left, because that means more ways to go back right. You only want to go this way or that way. How many ways are there to do so?
N plus M, choose M.
Number of paths is M plus N, choose N, which is the same as M plus N, choose M. Why is that?
Because you know you have to go up N times and you know you have to go over N times.
So there's always, no matter what the path is, M plus N moves. You gotta do M plus N moves. You gotta move N times to the right and N times up, no matter what the path is. But you can choose which ones are to the right. Out of, that's what you're saying, right? Out of the M plus N total number of moves, you get to choose at what step you move right. The other steps will be up. So that says out of total of M plus N moves, how many are right? Does M choose to the right? So how many paths I have on a grid? M plus N choose N. Any path will have to make N moves to the right and N moves up. So the total number of moves is M plus N. The choices consist in which ones of these M plus N are to the right, and the remaining ones will be upwards. So out of M plus N moves, here the M plus N moves, I can choose right, and then up. That will be the path, go all the right, and then go up. Or I could choose up first, and then right. That will be up, right. It only comes down to which positions are out of this M plus N moves, which ones are going to the right. Every different choice will correspond to a different path. This is a set choice because we're choosing M positions out of M plus N. These are not in order. I mean, the order is given by the path itself. Hands up who follow me. Good. What about if I have a square grid now? So square grid, this is N by N, 0 to N, this is N. So this is a square grid. Say it has 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Right? And I want to get from here to here, this is NN, paths from 0, 0 to NN. It's going to be just like before, N plus N is N, right? There's no difference between this and that yet. What I'm going to do here is to draw this diagonal. And I want to call restricted paths. Are the ones that do not cross diagonal. They stay down. So I have this diagonal. The paths that are valid now are not all the paths. This is a valid path. Because it stays down below the line. This is not a valid path if from here it goes up, which before was a valid path, right? Before I could have gone up. And now it's in here. This is an invalid path. So I want to count how many of those 2 to the n choose n paths, that's all the paths, stayed down That's not an easy problem. Yes?
Would this be half?
No.
Really consider half possibly?
It's actually very few, a lot fewer than half, because most paths will cross the diagonal. These number restricted paths, it's called CN, the Catalan number. And this is one of the problems that has as an answer Catalan number. There's 400 problems that have this answer. This is one of them. This number is actually not just, you're saying half, is actually 1 over n plus 1 of the total. You are implying it's half of it. If n here is 5, this would be the total number divided by 6. If n is 100, that would be about 1% of them, right?
Can you explain what Catalan number is again?
Is the number of blue paths.
Because would the problem be what kind of Catalan number?
So we have to prove that this is the answer to this question.
Oh, like that specific number.
This is the Cn, but Cn by definition is the number of blue paths. That's Cn. What we're going to prove is that Cn is exactly this value. So how do we do this? How can we prove that the number of blue paths? How do we compute the number of paths? I mean, proving that or computing the number of blue paths is the same thing, because we get the answer, we can check if it's that or not. What we need to do here, that's going to happen next time, is to say, I want to count the wrong paths instead. So that seems easier, the number of paths that cross this line. And then subtract them from the total, right? If I count the wrong paths, I can subtract them from the total. The way I'm going to count those, I need one of these bijection functions. I'm going to map the paths, the red paths, into something else, and then figure out how to count those. And then we'll do other problems that have the same answer, the Catalan number answer. I'm going to put a PDF online for those of you who can't wait until Tuesday. You have something to read about this path. Oh, attendance sheet, please. Where is that paper? First one.
Yeah, I remember that. Yeah. You got it. Yeah. It's Tuesday. It's Tuesday.